Understanding ECGs is not just about memorizing waveforms. It's about knowing exactly what those waves represent inside the heart, both electrically and mechanically. Electrical signals initiate mechanical action. Each part of the ECG shows us not just electricity, but a physical movement. Blood being pushed, chambers contracting, or muscles relaxing. Today, we are going to link each mechanical event to its matching electrical signal on the ECG step by step. Let's begin. The journey starts with the sinoatrial node, or SA node, the natural pacemaker of the heart. When the SA node fires, it sends an electrical impulse that spreads across the atria. This causes the atria to depolarize, meaning the heart muscle cells change their electrical state and prepare for contraction. Shortly after depolarization, the atria contract, pushing blood into the ventricles. On the ECG, this entire electrical activation of the atria appears as the P wave, a small, rounded bump at the start of each heartbeat. It's important to remember, the P wave represents atrial depolarization. The atrial contraction follows immediately after this electrical signal. Mechanical contraction lags just slightly behind the electrical depolarization. Section 2. The AV node and the PR interval. After the atria depolarize, the electrical signal reaches the atrioventricular node, or AV node. Here, there is a deliberate delay. This AV nodal delay is critical because it gives the ventricles time to fill completely with blood from the atria before they contract. On the ECG, this pause is reflected as the PR interval, the flat section from the beginning of the P wave to the start of the QRS complex. The PR interval measures the time taken for the impulse to travel from the atria to the ventricles. Key point to remember: PR interval equals AV nodal delay equals ventricular filling time. If the PR interval is too short or too long, it suggests problems with impulse conduction between the atria and ventricles. Once the impulse leaves the AV node, it travels down the bundle of His, into the right and left bundle branches, and into the Purkinje fibers. This rapid spread of electrical activation causes the ventricles to depolarize. Depolarization of the large, thick-walled ventricles results in a powerful mechanical contraction pumping blood to the lungs and the rest of the body. On the ECG, this event is seen as the QRS complex, a sharp, spiky wave. Because the ventricles have much more muscle mass than the atria, the QRS complex is larger and more dramatic compared to the P wave. Summary: QRS complex equals ventricular depolarization equals ventricular contraction. Problems in this phase, such as a widened QRS, can suggest delays or blockages in the electrical pathways of the ventricles. Section 4. Ventricular repolarization and the T wave. After the ventricles contract and blood is ejected, the heart muscle cells need to reset a process called repolarization. Repolarization restores the original electrical state of the cells, preparing them for the next heartbeat. This recovery phase appears as the T wave on the ECG. It's important to understand that repolarization is an active, energy-dependent process, not just passive relaxation. Thus, T wave equals ventricular repolarization equals recovery and readiness for next beat. Abnormalities in the T wave, such as inversion, flattening, or peaking, can indicate ischemia, electrolyte disturbances, or other pathologies. There are two critical principles that tie everything together. First, electrical events always precede mechanical events. You see the wave on the ECG first, then the actual contraction or relaxation happens slightly after. Second, disruptions in the ECG waveform often hint at mechanical dysfunction. For example, if the QRS complex is too wide, it may suggest delayed ventricular contraction. If the T wave is abnormal, it could indicate problems with recovery, like ischemia. By linking what we see on the ECG to the actual function of the heart, we can move beyond memorization and start thinking like true clinicians. Let's quickly summarize the key links. P wave, atrial depolarization, atrial contraction. PR interval, AV node delay, ventricular filling. QRS complex, ventricular depolarization, ventricular contraction. T wave, ventricular repolarization, ventricular recovery. Each phase is critical and each abnormality gives you a vital clue about what might be wrong inside the heart. In this session, we connected the dots between the electrical patterns we see on the ECG and the physical, mechanical actions inside the heart. Up next, we'll focus on something critical: timing. In ECGs, conduction speed shapes every waveform. Join me in the next module: Time is Everything, Conduction Speed, and ECG Waveform Patterns, where we'll explore how timing reveals hidden cardiac clues.